Hello, everybody. Welcome to the last session of this year, 2023, of our Quantum Computation and High Energy Physics seminar. It's a great pleasure to introduce Jad Halimeh, who just recently became an Emmy-Noether Research Group Leader at LMU in Munich. He's an expert in far from equilibrium gauge theories and gauge theory dynamics, and he's going to share today his results on the quantum simulation of such dynamics. So thank you very much, Jad, for accepting our invitation, and we look forward to hearing you.
My pleasure. So thank you very much for having me here. It's my pleasure to be back among friends and also to the audience on YouTube. Today I would like to present the overarching theme of my research, and which actually underlies the new research group that I have established here at the Ludwig Maximilian University of Munich starting last month. And basically, the umbrella under which my research falls is the quantum simulation of far from equilibrium gauge theory dynamics. So here we see three fundamental terms in this title that I will explain and dive into a bit more to show you why we are interested in this. So we see we have quantum simulation, that's one topic. Then we have gauge theories, and also they're far from equilibrium dynamics. Before we go into the details, let us discuss a little bit why we are motivated in this line of research. So the motivation behind this research field is twofold. First, there's the major relevance to high energy physics. So as we know, gauge theories are the staple of the standard model. For example, we know that we have the gauge theory of quantum electrodynamics, which describes the interaction of light and matter. Then there's also quantum chromodynamics, which is another gauge theory describing the interactions of quarks as mediated through gluons. Dedicated particle colliders are wonders of science and engineering that actually allow us to probe the inner workings of nature and gauge theories. And here I show you an example photograph of RHIC, the relativistic heavy ion collider at Brookhaven National Lab. And now in these particle colliders, what happens, we really probe non-perturbative far from equilibrium dynamics that is very hard to probe using classical methods on classical machines. As an example, let us consider heavy ion collisions. So we bring two lead ions and we collide them at such high energies that they disintegrate into their constituents, which are quarks and gluons. And now we find that in this interaction cross-section, the quarks very quickly bind back together and form hadrons. We really would like to understand from first principles exactly what happens here, why the quarks very quickly bind back together and form hadrons. Currently, this is probed using phenomenological models on classical computers, but these have fundamental limitations when it comes to probing this process here, which involves heavy entanglement buildup. And so we ask ourselves, do we have a complementary venue where we can actually obtain a quantum advantage, allowing us to naturally incorporate this entanglement buildup on the setup itself, which can also allow us to obtain temporal snapshots of the time evolution occurring here from first principles dynamics? The other point of relevance is that in quantum many-body physics, and in particular, the question of the equilibration of isolated quantum many-body systems. So usually when we think of thermalization, we always consider, or traditionally, we consider a system coupled to some kind of bath. But when we have an isolated quantum many-body system, we can think of equilibration and thermalization in terms of looking at subsystems of this global isolated quantum many-body system. And now through unitary time evolution, we see that there is entanglement buildup between the different subsystems of this isolated global quantum system. And at long times, these subsystems can exhibit thermalization dynamics locally, but they can also exhibit exotic non-thermalizing dynamics that really gives us a more thorough understanding of quantum many-body systems, how they thermalize or avoid thermalization completely. Currently, the best methods to study this question of the equilibration of isolated quantum many-body systems is tensor networks on classical machines. Despite tremendous progress in this field, these methods are mostly limited to one dimension when we are probing far from equilibrium dynamics, and we can go to quasi-one-dimensional systems. So we can think of a two-dimensional system where we are in the thermodynamic limit along one dimension, but then the second dimension has a finite number of lattices. So we are really still far away from the true thermodynamic limit in two dimensions. And as I mentioned, whether you are in 1D and 2D, you are limited to very short evolution times, again, due to this beast of entanglement buildup. That is the main ingredient of truly quantum many-body dynamics. And again, we ask this question, can we come up with a complementary venue that will naturally incorporate this entanglement buildup in the wave function itself, and that will allow us not only to probe longer evolution times, but also higher dimensions, where we would really be interested in understanding equilibration in quantum many-body physics and also in high-energy setups. Furthermore, would such a setup allow us to extract exotic non-thermalizing dynamics to use it for technological applications such as quantum metrology, for instance? To put things on a formal footing, let us consider a paradigmatic gauge theory, which is the Schwinger model. And this is nothing but one-dimensional quantum electrodynamics. So it's quantum electrodynamics on a discretized one-dimensional lattice. Here we see in this Hamiltonian that we have these staggered fermions, psi, that reside or that live on sites L. Between these sites, we see that we have links that are denoted by L comma L plus 1. So when you see L comma L plus 1, this is telling you that I have a link between the adjacent sites L and L plus 1. On these links reside gauge fields denoted by U and electric fields denoted by E. Now, the job of this gauge field operator U is simple. It sees that when matter moves, the electric field has to change in such a way that Gauss's law, which we know from electrodynamics, is conserved. Now, in this quantum many-body model, Gauss's law takes the following form. So here again, we see the locality of Gauss's law, which is here a discretized generator of the U1 gauge symmetry of this model. And when you hear a gauge symmetry, this is nothing but a local symmetry. So you know from your quantum many-body physics class that there are global symmetries. Let's think of the Bose-Hubbard model, where you have a U1 global symmetry, where the number of bosons in your system is conserved at any time. But a gauge symmetry, a U1 gauge symmetry, tells you that locally you have a conservation law. And this locality is what we call a gauge symmetry. And here you see it in this operator GL, which gives you an intrinsic relationship between matter occupation on site L, which is denoted by psi L dagger psi L, and the allowed configurations of the electric fields on the links adjacent to the site. So, which we call EL L plus 1 and EL minus 1 EL. If you look at this carefully, you will see that this is nothing but a discretized version of Gauss's law that we know and love from electrodynamics. So I have an electric field here, a gradient of the electric field, if we're thinking in one dimension. And this gradient has a direct relationship to the local matter occupation. Now, the U1 gauge symmetry of the Hamiltonian H naught is encapsulated in these commutation relations. So again, we see that we see the locality of the gauge symmetry in that H naught does not only commute with a sum over all the GLs, but it commutes with every generator GL at every site L. And we call gauge invariant states the simultaneous eigenvalues of all generators GL, with their eigenvalues denoted by small gl, which we call background charges. Usually, we want to work in one gauge sector, which is the sector of Gauss's law, or what we call the physical sector, where GL is 0. Now, a gauge superselection sector is defined as a unique combination of all these eigenvalues or background charges, GL, over the entire lattice. Now, since H naught commutes with all these generators GL, we can block diagonalize it in the basis of GL as follows. So here I pictorially denote a yellow block to represent a unique gauge superselection sector. And as I mentioned, we usually want to work in the superselection where all the G's are 0. And this is the physical sector or the sector of Gauss's law. However, as we will see later in the talk, it's interesting sometimes to work in several sectors together to see some really cool exotic dynamics. Now, I would like to realize this Schwinger model on a quantum simulator. So I just want to stick to one dimension, and I want to stick to one spatial dimension and try to map this onto a quantum simulator where I can probe the physics of this model in the lab. But a problem arises here in that in nature, the gauge and electric field operators have an infinite dimensional local Hilbert space. They're composed of infinitely many degrees of freedom. So if you want to work with this numerically on your laptop or in the lab, this requires a lot of engineering overhead. And so in a great work by Uwe Jens Wiese and Chandrasekaran, there was this formulation, so-called the quantum link formulation, where we map or we represent the gauge and electric fields as spin S operators. And the mapping takes the following form. As such, you are able to reduce this infinite dimensional local Hilbert space to a 2+1 dimensional one. And then you can choose a small s and say, okay, I only want to capture the low energy physics of the Schwinger model, and then you are safe. We will discuss this in more detail later. And now, because you are in one dimension, you can employ a Jordan-Wigner transformation, and you can get rid of these staggered fermionic operators psi and replace them with simple qubits or Pauli operators sigma z. So now sigma z at site L represents your matter occupation there. And this recipe gives rise to the so-called spin S U1 quantum link model, where now you see we have a hopping term in the matter, sigma plus, sigma minus, but we also have the gauge field represented by S plus, which acts on the electric field as Z in order to make sure that Gauss's law is always respected. And here we see M, this is the fermionic mass. We just replace psi L dagger psi L with sigma Z. And now let's see how we can map this model onto a quantum simulator. So we use the wise words of Richard Feynman, who told us that we better simulate such quantum many-body models using other quantum many-body models that we can implement in the lab. So let us again consider the Schwinger model. So it is composed of these matter sites, as I discussed in the previous slides. And these matter sites can either be empty, or they can be occupied with positrons or electrons. In between them, we have links that can either point to the left or to the right. This is the electric field. And here I'm doing a very simplistic model. I am discretizing the electric field as a two-level system. So I chose S, I told you I represent the gauge and electric field operators as spin S operators. Well, now I'm going to choose S equals 1/2. So it's a very crude toy model, but it's a necessary and important first step towards approaching the limit of QED. And so I want to try to start with this and implement it in the lab. Let us call H naught the Hamiltonian of the Schwinger model that describes the dynamics of this system. And as I mentioned, Gauss's law is defined on this constraint involving this matter site and its adjacent links, which is a discretized version of Gauss's law. And now what I want to do is I want to implement this model, which is described by this Hamiltonian, on an optical superlattice. So right away, you see that this term, the gauge coupling term proportional to G squared, is static in this situation. Because SZ for a spin for S equals 1/2, if you square it, it's nothing but a rescaled identity. So it's a static term, it doesn't affect your dynamics. Of course, this is a bit problematic if you want to use the gauge coupling as a confinement parameter, as a tunable confinement parameter, but we'll get to larger spin representations where this term does not vanish. So let us now try to map this model onto this optical superlattice. So here, I would like to have this following mapping, where the gauge field S plus is represented as a doublon creation operator, so B dagger squared, and the electric field is represented by this rescaled occupation, bosonic occupation operator on the side that would represent the link in the gauge theory. And for the matter, I'd have my creation operator as simply a bosonic creation operator, while my matter occupation is nothing but this rescaled local bosonic occupation operator. To put things more concretely, let us look at the allowed configurations of Gauss's law in the quantum link model and its corresponding representation on the optical lattice. So we see I have deep optical lattice sites here on which I can have 0 or 2 bosons, but nothing else. And I have shallow sites that represent the matter sites of the gauge theory, on which I can have a single boson or no bosons at all. So what do I need to do on my quantum simulator in order to achieve this mapping? Well, we look at the Bose-Hubbard model taking the following form. So here you see that I have introduced a staggering potential delta that allows me to have these deep sites that represent the links of the gauge theory and the shallow sites that represent the matter sites of the gauge theory. But now I want this 0 or doublon constraint on the deep sites and the 0-1 constraint or hardcore constraint on the matter sites. It turns out that if you go in the regime of on-site repulsion strength U and staggering potential delta, much larger than the hopping term J and an overall tilt delta, you end up obtaining your gauge theory up to leading order, well, up to second order in perturbation theory, but you also get some smudge, if you wish, so sub-leading terms that explicitly break Gauss's law GL. However, as I will describe, this tilt delta is crucial to include a stabilizing term on our quantum simulator that actually suppresses the growth of gauge violations up to all accessible times experimentally and numerically. I will discuss this more on the next slide, but now the upshot is once you go into this regime, you are able to have a nice and beautiful mapping between the Bose-Hubbard model, which is the natural Hamiltonian describing the interactions of bosons on this optical superlattice, and this gauge theory toy model that we are interested in. And the parameters of the gauge theory, kappa, so the tunneling of the gauge theory, and m, the mass of the fermions, are related to the parameters of the Bose-Hubbard model in the following form. Good. Now let us talk about the stabilizer term. So as I told you, up to leading order in perturbation theory, we get from the Bose-Hubbard model the gauge theory, the target gauge theory H0, but we get unavoidable errors, lambda H1. But this linear tilt delta introduces a protection term VHG, which is nothing but a linear weighted sum in the generators of the gauge symmetry GJ. Now, from a theoretical point of view, if you choose your coefficient CJ properly, you are able to energetically isolate the subspace of the target gauge theory, so where the H0 physics occurs, from all the other sectors where lambda H1 wants to couple my target subspace. And you are able to show analytically and numerically, as we show in this PRL and this PRX quantum, that you are able to suppress gauge violations proportional to lambda squared over V squared for all experimentally and numerically accessible times. And your dynamics will be represented by this Zeno-Hamiltonian. And here, Paolo Facchi is the master of this. And of course, Professor Pascasio, they basically showed how you can employ the concept of quantum Zeno subspaces by employing these coefficients Cj in a proper way, where now your effective Hamiltonian is nothing but your target Hamiltonian H naught plus lambda P naught H1 P naught, where P naught is your projector onto the target sector. So it's the projector that keeps you in this target subspace where your physics wants to be. So usually H1 is a term that completely removes you from the target subspace. So this term would be 0. But sometimes you can have undesired gauge invariant terms within H1, which would just renormalize your gauge theory, but that's not a problem. And so at the end of the day, what you get is the following phase diagram. So if we fix the error strength lambda and we vary V, we see that when V is quite small, so when my stabilizer T term is negligible, we have an uncontrolled violation regime where if I vary V slightly, I just get a completely different error. I don't have like an analytic relation between the error and the value of V. While if your V is sufficiently large, and here I'm talking of the order of lambda, so experimentally very accessible, you end up entering a controlled violation regime where your infinite time gauge violation scales as lambda squared over V squared. Analytically, you can show that this can happen up to times exponential in V if you choose your Cj coefficients properly. Good. So now let us see how we can use this finding to actually realize some interesting gauge theory physics in the lab. So we took this gauge theory toy model and we wanted to probe the so-called Coleman phase transition of the Schwinger model. Basically, we start at negative infinite mass, where every matter site of your gauge theory is occupied. So here you see a proliferation of matter, where you have an electron on every odd side and a positron on every even side. And now we slowly tune the mass from negative infinity to positive infinity, where we go adiabatically from this charge proliferated phase to a symmetry broken phase, a global symmetry broken phase that encapsulates the two vacua of QED in one dimension, which you see here. We tuned this quantum phase transition on our quantum simulator, so I'm talking in experiment, using a 71-side optical lattice. And you see that in this case, you can convince yourself that the gauge protection term or the gauge symmetry stabilizer term takes this following explicit form. And it allowed us, for the first time ever, to certify a controlled gauge invariance on a quantum simulator, where here you see that we measured the gauge violation using projective measurements up to the entire duration of the experiment. And we see that it's suppressed below 10% at all times, which is something that is quite good because it allowed us to really see something that we know theoretically exists, which is the Coleman phase transition. If you want more details, this is published in the following Nature article. We then used this quantum simulator to look at the thermalization of gauge theories. This is something very relevant, and it's an open question, especially when it comes to the thermalization of heavy ion collisions, which actually occur at much faster timescales than naive scaling arguments predict. Of course, here again, I remind you that we are using a one-dimensional toy model gauge theory with a crude two-level representation of the electric field. But again, as I also mentioned, this is an important and necessary first step to achieve these large-scale quantum simulators where we can really probe collider-relevant physics. And here what we did is we chose different initial states that only have in common the quench energy, the initial quench energy. And based on this, we quench these generic initial states, and we see that so long as they have the same quench energy, they relax into a steady state that can be described by a thermal ensemble. And so we can actually extract a temperature for these quenches. And here I show you two plots, one corresponding to an infinite temperature quench and another one to a finite temperature quench. And you see good agreement between the steady state that is reached, and the predicted value from the corresponding thermal ensemble. Details on this experiment and the analytic support of it can be found in the Science article. And then what we did is we said, okay, good. We see here, as you see, we have quick relaxation of local observables. So here you see that your local observable starts at a really large value, and then it very quickly relaxes to a steady state, right? You see barely 2 oscillations, and then it relaxes. But can we do better? Can we tune our system in such a way that I have persistent oscillations up to all experimentally relevant times that, can give me more insight into how I can avoid or violate the eigenstate thermalization hypothesis? So we ended up looking at quantum many-body scarring. This was first discovered by the group of Misha Lukin in 2017, where they had an Ising-like quantum model, and they found that for a certain special state, if you quench it at 0 mass, you end up getting these persistent oscillations. They did some really nice finite size scaling analysis for it experimentally and using matrix product states, and they saw that these oscillations did not decrease with system size. So it was not a system size effect. And they were basically baffled until there was a very nice paper by Federica Soracci that actually explained what was happening. They showed that this quantum many-body scarring, if you want to think about it from a gauge theory perspective, is the spontaneous creation and annihilation of electron-positron pair from the vacuum. And so here we used our quantum simulator to probe this in more detail and to much longer evolution times, thanks to the stabilizer term that I explained earlier based on quantum xenodynamics. And indeed, you see here that if you start in a special initial state and you quench at 0 mass, you end up getting oscillations in your order parameter. So here, this corresponds to the flux, right? You start in the vacuum of QED and you quench to 0 mass, and you see that your flux really oscillates between 1 and -1. Of course, you have damping, but these oscillations persist much longer than the oscillations that you see here. It turns out the reason this happens is that your initial state has a large overlap with so-called quantum many-body scars. So forget about the black dots, just think about the red process here. So here I'm showing you the overlap between the initial state Z2 in which I prepared my system and the eigenstates of this Hamiltonian. You see that you have a rainbow here of equally spaced, in energy, equally spaced eigenstates that have a huge overlap with this initial state, but that have anomalously low bipartite entanglement entropy, as you see in the lower panel. So what this means is that I have a cold subspace of special eigenstates that are not thermal. And if you prepare your initial state with a large overlap with these eigenstates, you end up delaying or avoiding thermalization up to really long times. So up to all experimentally and numerically relevant times, even though you are in an ergodic system that should, in principle, thermalize. Mind you that these quantum many-body scars grow polynomially in system size, so they're exponentially suppressed by the remaining thermal eigenstates of your ergodic model. But nevertheless, if you are able to tune your system properly, you will see this non-ergodic dynamics, which is quite interesting from a fundamental and technological point of view. And we were able in this experiment, which is published in PhysRef Research, we were able to show that scarring actually can exist in many other regimes than in this specific special quench and special initial state. We actually find that there's a plethora of scarring regimes in this toy model, and actually we showed theoretically that it also exists for larger spin representations of the electric field. But I don't have time to go into this in much detail, but I would be very happy to discuss it with you after the talk. And then we wanted to look at further exotic gauge theory dynamics, such as confinement. As you know, confinement in high energy physics and in condensed matter is a very hot topic. So what we did here, as you know, we cannot have a gauge coupling term because we are at a spin 1/2 representation of the gauge and electric field. So what we do is we introduce the so-called topological theta term. And the way we do this is by introducing an extra staggering between the deep sides of the optical lattice. In terms of the gauge theory, what this does is it introduces an explicit symmetry breaking term. It breaks explicitly CP conservation in your gauge theory. And what that translates to is a penalty on the growth of an electric string between an electron-positron pair. And the strength of this term is denoted by chi, which is nothing but the detuning between the gauge sides of your quantum simulator. And so intuitively, what should happen is the following. When this term is vanishing, so chi is 0, an electron-positron pair prepared on top of vacuum will just propagate ballistically. There's no penalty on them going far away from each other. And indeed, that's exactly what happens. But now when you tune chi to larger values, you see that this electron-positron pair is glued to each other up to all experimentally and numerically accessible times. Using a quantum, so the theory behind this was published in this PRX quantum, and using a quantum gas microscope with our colleagues in Hefei, China, we were able to measure the length of this electric string at various values of chi. And we got the following really beautiful result. So you see that whereas when chi is 0, so when your topological term is vanishing, you see that the length of this electric string grows ballistically over time. But as you tune this term to larger and larger strengths, you see that the electric string length sticks to its initial value up to all times, experimentally demonstrating confinement. And this term and this experiment is has appeared recently on the archive, well, half a year ago, so not so recently, and it's now under consideration in Nature. Good. So now I have shown you the Stoy model in one dimension and with a two-level representation of the electric field. But of course, if I want to simulate gauge theories that are relevant to particle colliders on my quantum simulator, I need to go to higher spatial dimensions, and I need to go, well, 3 spatial dimensions ideally, and I want to go to higher representations of the electric field. So 2 levels is not enough. And so we came up with a proposal where we are able to realize scalar quantum electrodynamics in 2 dimensions, but with a 2-level representation of the electric field. And here I show you the mapping between the quantum link Gauss law allowed configurations and their corresponding mapping on the Bose-Hubbard model. I show you this for positive infinite mass, where you don't have any matter, and for the negative infinite mass, where matter occupies your site. And what we did is we made this proposal, and we benchmarked it using matrix product states on a cylinder. So this cylinder has an infinite extent along the axis, but it has a finite width where we employ periodic boundary conditions. And we were able to go to 6 matter sites, so effectively 12 sites in total. And what we did is we again did the sweep to look at the Coleman phase transition. So we go from a phase where every matter site, this is the vertex of this square lattice, every matter site is occupied. And we tried to go to a vacuum state where every matter site is empty. So as you see, we are able to do this on the Bose-Hubbard quantum simulator, but numerically. So here, this is not an experiment. This is actually being built right now in Shenzhen with our colleague, our experimental colleague, Bing Yang. And here, what is interesting is you see that, so here you see you have 2 bosons on this link, and the other links are empty. So you see, if you look at the legend here, or at the color bar here, you see that the other links, which correspond to this and this, they're completely empty because I'm in a charge proliferated state. And so now if I go adiabatically here, what I should see is that this link is occupied, but I have an equal probability that this link gets occupied, right? So these 2 bosons can come here instead of these 2 bosons coming here. So I have a huge degeneracy in the vacuum that I don't have in 1D. And this is why you see that these links here are not completely red, they're orange, right? So they have a quarter occupation of a doublon rather than a full one, and that's because of this degeneracy. We also, in one dimension, we looked at higher representations of the electric field, and in particular, we looked at a spin one. So we have a mapping where we can do it for any spin S, but for something that is experimentally feasible in ultra-cold atoms, particularly in dipolar atoms such as erbium and dysprosium, we looked at a spin 1 representation of the electric field. And this is the mapping between the quantum link model allowed configurations based on Gauss's law and their corresponding maps in the Bose-Hubbard quantum simulator. So here, very simplistically, if you look at the deep lattice side, you're allowed to have 0, 2, or 4 bosons. And this would correspond to the electric field eigenvalues -1, 0, and 1, respectively. But on the matter sides, again, you can only have 0 or 1 boson. So again, you have this hardcore constraint. And again, using matrix product states, we benchmarked the quantum simulator, the proposed Bose-Hubbard quantum simulator, to the actual quantum link model that we are interested in probing. And we see that we have really great agreement whether we look at the chiral condensate or the flux. And as you see, Gauss's law is extremely well suppressed. So it's very close to 0 up to all simulation times. And this is, again, thanks to a tilt that we employ that brings about this stabilizer term thanks to quantum xenodynamics. And here, something that we are able to do that is not possible with the spin 1/2 representation is tuning confinement, tuning the gauge coupling to induce confinement. So here I show you 2 columns, one for confinement on the quantum link model itself, and one on the proposed Bose-Hubbard quantum simulator. And all these results, again, I repeat, are done in matrix product states, so nothing is experimental here. And you see that when you have the vanishing gauge coupling term, an electron-positron pair here, which we prepare on top of vacuum, very quickly and ballistically propagates away from each other, and you don't have any confinement. But if you go to a strong gauge coupling term, you see that the propagation of the electron away from the positron is now penalized because the electric string between them causes an energy penalty. And you see that you have confinement up to all numerically accessible times. Good. And now, if I have enough time, I would like to talk to you about the local pseudo-generator for a different gauge theory. So somebody who has been paying attention would say, okay, look, this stabilizer term that is easy to implement in the U1 quantum link model is not so easy to implement when you have a more complex generator of Gauss's law. And this brings us to the topic of the Z2 lattice gauge theory. So here again, I have matter degrees of freedom denoted by hardcore bosons, or you can think of them as qubits. And I have a gauge field described by this operator tau z. And I have an electric field described by this operator tau x, which are also qubits. But now you see that unlike the case of the U1 quantum link model, where the generator of Gauss's law was composed of single body terms, which experimentally are very cheap, I have a nasty 3-body term, which is extremely hard to implement, whether on a digital platform or on an analog platform. And indeed, initial attempts to realize this gauge theory were basically restricted to small building blocks, because going to larger building blocks had no chance of being actually realized because of gauge violations. So we came up with the idea of the local pseudo-generator. So what we do is we split this 3-body term into a sum of a 2-body term and a 1-body term. And the really interesting thing here is that if you work in the sector of Gauss's law, in the physical sector, you will not be able to distinguish between Gj and Wj. So here, Gj can only have 2 eigenvalues because it's a Z2 gauge symmetry. It can either have +1 or -1. So if you focus on +1, so Gj tar is +1, you see that whenever Wj is +1, Gj itself is also +1. and the same when your gauge sector locally is -1. So what this means, whenever I'm in the target sector of Gauss's law, I am not able to differentiate between Gj and Wj. And so I can update my gauge protection term as follows. So I can just remove Gj and put Wj in its stead. And again, I get the same physics thanks to the beautiful quantum xenodynamics concept. And I can again isolate this target sector from all other sectors. However, so you can trust me, I'm not going to show you results, but you can trust me that we get the same stabilization of the Z2 gauge symmetry as we did for the U1 gauge symmetry. And we did this numerically and analytically, and you can find it in these papers as well. However, something really interesting here happens if you go to initial states that don't just live in one sector, but a multitude of sectors. Allow me to explain. Let us consider the concept of disorder-free localization. So here I show you two states. Both of them have the same matter configuration. So that here I'm using only 4 matter sites for illustration purposes. So the left 2 sites are occupied with matter, while the right 2 sites are empty. And now, if I prepare my system in the physical sector of Gauss's law, I expect that after a quench, I should get an equal probability of finding a boson at any site at really long times. On the other hand, what happens now if I take the same matter configuration, but I prepare my initial state as an equal superposition over all sectors, over all gauge sectors? What happens to the imbalance at long times when I look at the difference between the matter occupation on the left half and the right half of the lattice? Well, here are the results. So you see that whereas psi naught x, which lives only in the sector of Gauss's law, my imbalance goes from its maximal value of 0.5. So here I'm normalizing by the number of sites. It goes very quickly to 0 and stays there. However, if I start in psi naught z, which by just aligning the electric field along the z direction, I get an equal superposition of all gauge sectors. So this state lives in all gauge sectors simultaneously. You see that the imbalance never quite goes to 0. So I am retaining initial memory of the initial state up to all times of my quench dynamics. Now, this is very remarkable for one major reason. Everything here is homogeneous and disorder-free. So we know from many body localization that usually you need disorder over space and some parameter in order to retain memory of your initial state. But here I don't have any disorder in space. It turns out, as shown in these beautiful papers by the Musna and Skardikyo groups, this superposition state, what it does is it samples the background charges of an extensive number of gauge superselection sectors. And so you have an effective disorder over background charges in the Hilbert space. And this is what induces this localization. But again, there's no spatial disorder, which makes this a very interesting property. However, this is in an ideal world where you don't have experimentally unavoidable errors. So again, let's start with the superposition initial state. And now let us include experimentally feasible errors that couple these different gauge sectors together. And without any protection, you see that even for a teeny tiny error strength lambda, which is 100th of your energy scale, you see that your disorder-free localization completely vanishes. But here, as we show in this PRX quantum xenodynamics comes to the rescue again, but not just that, it will not only restore disorder-free localization, it will enhance it, and I will explain why. So you can prove through quantum xenodynamics that if you include this protection term based not on your full generator of Gauss's law, but on the pseudo generator that I explained earlier, you end up getting the following Zeno-Hamiltonian, which now is your stabilizer term plus your original target model, but projected onto the different gauge sectors of the pseudo generator Wj. Interestingly, the pseudo generator Wj has a gauge symmetry that is richer than the Z2 gauge symmetry that we started in. So whereas the Z2 gauge symmetry has sectors denoted in yellow, the gauge symmetry generated by the pseudo generator is denoted by these green blocks. What this means is the following. When you are in a green block, you automatically are in a yellow block, but not vice versa. So this shows you that WJ has a richer symmetry. But what does this mean now? So it means that our superposition state becomes dynamically a superposition over an effectively much larger number of gauge sectors. So whereas we started as a superposition over the yellow blocks, dynamically, I am now effectively in a superposition over a much larger number of green blocks. So I have a lot more background charges over which I'm disorder averaging. And what this does is it leads to much richer disorder-free localization. So here in the original ideal target model, you end up retaining 20% of your initial state memory. When you add the local pseudo generator, you end up retaining 80% of the memory of your initial state. And in this PRX quantum, we also proposed a Rydberg atom setup where we can test this in a very feasible way. So what we did is we said we don't want to bother with implementing a three-body term. We just want to focus on a Rydberg setup that actually implements first and foremost the local pseudo generator. And this is done by arranging the Rydberg atoms in the following form. So the blue ones denote the links, while the gray ones denote the matter degrees of freedom. And now, by inducing a weak driving potential, I am able to induce dynamics. Now, this will not be exactly the Z2 gauge theory that we are interested in, but effectively, we will get a Z2 gauge theory, because now, even though I will have gauge non-invariant dynamics, my pseudo generator term is so strong that it will suppress gauge violation dynamics, as we proved numerically and analytically. And you see now that if I start in a gauge invariant state, my imbalance again goes to zero. So this is exact diagonalization results, but this is based on an experimental platform that we proposed. And now if you start in the gauge non-invariant superposition state, you see that you end up getting localized dynamics in the form of a finite imbalance. And this is within timescales that are accessible in current Rydberg atom setups, such as in the Misha-Lukin group. So I'm a bit over time. I will skip some proposal that I had on non-Abelian gauge theories, and I would like to thank my brilliant colleagues, so especially the groups of Philip Hauke, Fabian Grust, Johannes Knolle, and Zlatko Papic, with whom we have had a lot of really beautiful adventures in the world of gauge theory, quantum simulation, and far from equilibrium dynamics. And of course, our experimental colleagues, Zhenshen Yuan and Jianwei Pan in Hefei, China, with whom we have done several experiments where Bing Yang led the effort. Now Bing is a professor in Shenzhen, China. And of course, we have our local experimental colleague, Monica Eidelsburger, with whom we are exploring a lot of beautiful setups that we can realize using cold atoms. And as Yasser mentioned in his gracious introduction, my own research group started in Munich on November 1st, and we have several PhD positions open. So if you are interested and you have some experience in gauge theories, we would be happy to talk. Thank you very much, and I open to your questions now.
Thank you very much, Jad. Very nice talk, really impressive body of work, really excellent. Thank you so much for sharing with us. So we have a few minutes for questions. Yes, João, please. João, you unmuted yourself. You want to ask?
No.
Okay.
No questions? I guess the talk was just perfect. Everybody understood everything, right?
No, actually,
it is true.
Okay, I see Huri.
Huri, yeah, has a question.
Huri, please go ahead.
Huri, you need to unmute yourself.
Yes.
Hi.
Yes, sorry for delay.
No problem.
My question is that your the gauge symmetries that you have implemented are mostly sort of sorry. Can you implement non-commuting gauge symmetries?
Yeah, so you mean non-Abelian?
Or non-Abelian, yes.
Yeah, exactly. So excellent question. I mean, unfortunately, I ran a bit over time. So we do have a proposal for non-Abelian gauge theories using ultra-cold polar molecules. And the trick here, so the name of the game of the research that we do when it comes to mapping gauge theories on quantum simulators is to focus first and foremost on implementing the gauge symmetry before anything else. So we care more about the stabilizer term than the microscopic terms of the gauge theory. So in this ultra cold, so let me just show you the slides. So that's a good excuse for me to show what I was not able to show. So here, what we do is the following. We employ ultra cold polar molecules on the following vertex. So we have this honeycomb architecture where the x's denote matter sites and the circles denote so-called Richland sites. So the link here in a non-Abelian gauge theory, if you use Uwe Jens Wiese's brilliant quantum link model formulation, you see that you can represent links as composed of two Richland sites. Every link is composed of two Richland sites. And these Richlands are basically what discretizes your electric field. So now what I can do is I can look at a vertex, and this is the vertex where I want to stabilize Gauss's law. So what do? I use ultra-cold polar molecules that have naturally occurring dipole-dipole interactions. And now with a proper flow case sequence, I can convert these interactions into Heisenberg couplings. And I can engineer my parameters such that I live in the SU2 color singlet. And you see, these are the configurations of the allowed configurations based on Gauss's law that you see here. So now I realize an SU2 gauge symmetry locally. And as you know, this is non-Abelian. And now what I can do is I can bring these vertices together such that I induce tunneling between them. So this is one vertex. I just bring it close to the other vertex. And as long as my tunneling T is much smaller than the Heisenberg interaction strength J between all these four guys, then I am guaranteed to have a stable non-Abelian gauge invariance up to all accessible times. And let me show you here what I mean. So here T is the tunneling strength and J is the Heisenberg interaction strength. And you see dynamically, I get the following relation. So here, the error, the infinite time error scales as T squared over J squared. So the tunneling squared over J squared, right? This is the gauge violation at infinite time that well, over all times, but you see it plateaus to T squared over J squared in the infinite time limit. Does this answer your question?
Yes, sure. Is it possible that I ask a short other question?
Yeah, of course.
Yes. Regarding, at some point you talked about adding a term which essentially you break the CP symmetry.
Yeah.
This is equivalent to adding some sort of action in the model. Now, I don't know, have you worked a little bit more on how this process can be controlled? Can you really simulate a sort of action field and probably topological effects on the that it may produce in the
So that's a very good question. So here, exactly, it's as you say. So this CP violating term that we introduced, this is the topological theta term, right?
Yes.
And
exactly.
it breaks this CP conservation, which is equivalent to a global Z2 symmetry. It corresponds to a global Z2 symmetry that you have in these spin SU1 quantum link models. And this is similar to the topological theta term that you get in 3+1 dimensional QCD. Now, this axon field, I'm not an expert in it, and it was introduced as a means of solving or getting around the CP violation. I don't have a clear idea of how to implement this in 1+1 dimensions, but it's just that we haven't actively, we had a lot of other immediate ideas that we wanted to pursue based on this angle in upcoming works that I did not mention here, but maybe an axon field is something that we would consider in the future.
Thank you very much.
My pleasure. Thank you for your questions.
Thank you very much. So we're approaching the end of the seminar, but let me check. Are there any other questions? So if not, so we need to close. So let me thank again Jad for this great talk. Thank you very much. It was really interesting and impressive. It was great having you here. I don't know, Rafaela, I just want to, we should just show the slides with the organizers.
Yes,
right?
yes, for sure. I will give you a Dropbox link because yeah, it's too big over email.
Sure.
But,
yeah. So thanks again, Jad. I want to also acknowledge the co-organizers of the seminar, and in particular Rafaela and Matteo, who set this whole thing up, make sure this online logistics works. And so this was the last seminar of 2023, but we will continue in 2024, and we will soon be sending that information around. So if we don't see each other again, I want to thank again all of you for participating and wish you happy holidays, happy 2024, and hope to see you in our next session in January. Thank you very much. Have a good day.
ciao.
Thank you. Bye.